Hello and welcome to the video lecture series brought to you by St. Andrews Institute of Technology and Management. My name is Ravinder. I am an assistant professor with ATC department and we are discussing the subject called Data Structures 2 or Advanced Data Structures. And today we are going to start a new topic called heap sort. And I am going to divide this particular topic into two lectures, otherwise there will be much more of the data or much more of the information that has to be grabbed in a single lecture. So I'll try to divide this particular topic called heap sort into two. In the first one, in the first lecture that is today, we are going to see how we are going to deal with the heap. Heap is a type of data structure. Okay, we're going to discuss this in a few minutes. And in the next lecture, I'm going to deal with how to sort using that particular data structure called as heap. Okay, so I've divided the heap and the sort into the heap topic and then the sorting topic. So tomorrow, in the next lecture, we're going to see how to implement the sorting technique using the heap data structure. Okay, so let's move ahead to the notes. Okay, so let's start with now heap sort is a popular and efficient sorting algorithm in computer programming. Now, learning how to write a heap sort algorithm actually requires the knowledge of two type of data structures, that is arrays as well as trees. And I think you must be familiar with arrays and trees already. Now, the initial set of numbers that we want to sort in the array is the 3, 10, 3, 76, 34, 23, 32. And after sorting, we must get the array like 3, 10, 23, the sorted array one. Now, heap sort works by visualizing the elements of array as a special kind of complete binary tree called heap. Now, heap is a type of data structure which is actually a binary tree but have a few constraints on it. That is, few rules, few extra rules applied to complete binary tree. Okay, so the prerequisite for understanding the heap sort algorithm would be the complete binary tree, that is, what is the complete binary tree and what is the heap data structure and how to deal with it. So in today's lecture, we are going to focus on the heap data structure because I think we are already done with complete binary tree in the first unit. Okay. Now, relationship between the array indexes and tree elements. Now, complete binary tree has an interesting property that we can use to find the children and parents of any node. Now, let me again talk two lines on complete binary tree. Complete binary tree is just a binary tree, but in complete binary tree, we try to fill the or you can say the one rule that has been applied there is apart from your leaf nodes level, all the levels are completely filled. Okay, in ordinary binary trees, we don't have such kind of rules or constraint, but in complete binary tree, all the levels instead of or apart from your leaf node level would be completely free, and inside the leaf node level, okay, inside the leaf node level, we'll try to group the data as left as possible, as left as possible. Okay, so you can see here now this is a complete binary tree of sort. You can see the leaf level, that is this one, is not complete. We still have one position left, but all the other levels, that is the root level and the level above that, below that, are completely filled. And as you can see, this 10 could be here in this position also, that is the left child, the right child of 9, but we have tried to insert the 10, the element 10 to as a left child of 9, because the second constraint of your complete binary tree is the data must be accumulated to the leftward as much as possible. So anything which will come, we'll try to first insert them starting from the left hand side. Okay, so that is why 5, 6 and 10 are on the left hand side of the, or you can say are accumulated towards the, or are biased towards the left hand side of the tree. Okay, so I think you are familiar now with what the a complete binary tree will look like. So now we have a relation between how to find the children's and parents' indexes in a complete binary tree. Now this rule is actually implementable only for complete binary tree and not for any let's say general binary tree. So please keep that thing in mind. The rules we are going to discuss here is implemented only on complete binary tree only. Okay, and none other than that. Okay. Now, if the index of any element in the array is I, the element in the index 2 multiplied by I plus 1 will become the left child, and the element 2 multiplied by I plus 2 index will become the right child. Okay, so if you are sitting at the element of index I, and if you want to find out the indexes of its left hand child and right hand side child, all you have to do is to calculate the indexes using these two formulas. That is it. And if you are setting on a particular element I or of index I, and if you want to find out what would be the parent of that element, so I minus 1 divided by 2 would be the formula to calculate. Of course, you have to floor this value. I think we have discussed what is the flooring and ceiling in detail, or you must be know that. And that is downgrading the or the slash or dashing the value after the decimal and downgrading it to the lowermost. No, sorry, the lower and the closest possible integer. So if that is 3.5 is your number, then you will have to shed the element zero point 0.5 and round the value to the closest lower integer, that is 3. Okay, so these two formulas will be used to find out the parents or either child. Okay, so I've shown you here a complete binary tree and also in the array form at which index what is the element. So 0 being your 1 being your root node, so that is why it has been indexed as 0, and 10th being your last last leaf node, or the leaf node with greatest index, that is 5. Okay, now if you want to find the parent of this particular uh, node, that is the leaf node 10, its index is 5. I can implement the formula, this one, that is 5 minus 1, that is 4, divided by 2 will be equal to 2. As you can see that the element at index 2 is actually the parent of element at index 5. So I think this formula is correct in finding out the the parent. We can again take an example. Like this element 6 is at index 4. Now to find out the parent of this particular node, let's implement this particular formula, that is I minus 1 by 2, that is 4 minus 1, that is 3, and 3 divided by 2 is 1.5, and we are going to floor it. So the element that will, or the index that will came out, will be equal to 1. And as you can see here visually, the element that is 12, which is at index 1, is actually the parent of the node 6, or the element at 6. So I think we have our formula for finding out the parent is correct, and in the similar way you can find out the elements, the left and right hand childs of of any element using this formula. Okay, if there exists some. Okay, so I'll move on. You can, I think notes are with you already, so you can try to solve these equations. Now we'll move on to heap. Now heap is a special tree based data structure. A binary tree is said to follow a heap data structure if it is a complete binary tree. First constraint, we have already discussed what a complete binary tree is. And second, all the nodes in the tree follow the property that they are greater than their children. That is, the largest element is at the root, and both its children and are smaller than the there must not be and here, there must be or there. Both its children should be smaller than the root, and so on. Okay, such a heap is called max heap. And if you follow an inverted rule, that is all nodes are smaller than their children, then it will be called min heap, that is minimum heap. But for heap sort, we need maximum. So we'll focus on maximum. I have mentioned two examples here of max heap and min heap. As you can see, both of these are complete binary trees because the levels, apart from the leaf node levels, are completely full and the data is accumulated to the leftmost as possible. Secondly, every root node or every node is greater than its children's. So 12 is greater than 10 and 9. Again, the 10 is greater than both of its children, that is 5 and 6, and 9 is greater than its children, only children, that is 1. So this is your max heap. So as you move from leaf nodes to the root node, you will find values greater than the children itself or the previous node itself. And the inverted one will be the minimum heap. That is the greater the nodes, that is the parent node must always be less than its children node. Sorry. So one is actually smaller than its both of its children, that is 5 and 9. So that is minimum heap, but we are not concerned with minimum heap here. We're concerned with the maximum heap. Okay, so let's move ahead. Now the question arises, how can you convert an ordinary complete binary tree into an heap or max heap? And the function which actually does that is called heapify, or the process by which a complete binary tree is converted to a heap or the max heap is called heapification or heapify. When I say that I have to heapify a tree, that means I am going to convert the complete binary tree into a max heap. Okay. Now, starting from complete binary tree, we can modify it to become a max heap by running a function called heapify on all the non-leaf elements of the heap. Now, since heapify, let me again tell you that heapify is going to use recursion. So if you people are not comfortable with the recursion, so I must insist that you should go back and try to read about the recursion for a bit, because if you're not familiar with the recursion, then it is not going to make much of a sense how I have implemented this particular function called heapify. Okay. Uh, okay, let's move on. So the function heapify will be passed with an array, and the first element of the array will be called as root, and then we are going to find out which one is the greatest value, that is the root or one of its child. Okay, so a function will be called largest. This particular function largest, all he has to do is to find the maximum value of the three, that is the array 0, that is the root, the array 2 multiplied by 0 plus 1, that is 2i plus 1, which we have used to find out the left child of the root, and the array, there must be comma here, the array 2 multiplied by I plus 2, that is the right hand side child. We have seen these formulas here, so don't get confused. We have seen these formulas here. Let me show you them again. I haven't done anything new here. Now these are the two formulas to find the left. If your root node is at I index, if you have to find the index of your left hand child, you have to use this formula, and if you have to find the index of your right hand side child, you have to use this formula. So don't get confused. We have already done that. We're done with it. So we have, what we have done is, we have let's say let's pass a small array with only 3 elements, that is 7, 2 and 4, and I have passed the array to the heapify function. And what heapify function will do is, it will first assign the element at the 0th index, which is 7, as the root. Okay, and then I will this particular heapify function will try to calculate the largest of the 3 values, that is the root, its left hand child and its right hand side child. So the largest will have actually the element which is the greatest of all these 3, and if root is not equal to largest, that is if this particular element is not the largest, then we are going to swap the largest with the root. Now in this case, as you can see, the root is already the largest, but in the next scenario, let's say in this case, this array will be passed, root will be assigned as 2, and the function largest is going to find out the largest value. The largest value will came out of 3 will be 7, Now the index of 7 is not equal to the index of 2. That is root. So what we are going to do is we'll call a function called swap. Swap is nothing but it is just going to swap this the value at this index with the value of this index. Then 7 and 2 will be swapped. Okay. So 7 will go there and 2 will came down. And in this case, I think this is wrong. 7 must be here and 2 must be here. Okay, so you must correct that. 2 must not be here. It must be 7 here and must be 2 here. Okay, so I think you have got the point. Just ignore this last one. You can correct this one by writing 7 here instead of 2 and 2 here instead of 7. So please correct that. Now heapify base cases, as you or if you people are familiar with the recursion function, you must be familiar with the recursive cases and the base cases. Okay, so I'm not going to deep down into it. Now the example of shows two scenarios, one in which the root is largest element and we don't need to do anything, and another one is in which the root has a larger element as a child and we needed to swap to maintain the max heap property. Okay, if you have worked with recursive algorithm before, you have probably identified that this must be the base case. We have only three elements. If we have sorted all those three elements according to the heap constraints, then we are done with it. So this must be the base case. In the recursion, we have a base case. Base case is the case upon arriving which we have to stop. So this is the base case. We have to stop when we have arrived here. So let's move ahead. So this is of a larger example. Okay. So in recursion, you can see that in this particular case of a complete binary tree, if I want to convert it into a, let's say, max heap, then I have to keep my faith that the left subtree and right subtree are already max heaps, which is in this case is already there. So all I have to do is I have to switch the greatest value of these three to the top. Okay, as we have discussed a few seconds ago, the heapify function will be called and it will try to analyze which one is the greatest value or the largest value, and it will try to swap the largest value with the root. So what we have done here is the heapify function will try to calculate the largest value. It will call the function largest and it will find out that 10 is the larger value than its root, or the largest value of all three, and so 10 will be swapped with 2, and there you can see now 10 is swapped with 2. Now this particular portion here is actually now a heap, but now the problem arises with this left subtree. This left subtree now doesn't follow the rules of max heap because 2 is actually smaller than 5 and 6 both, and in the further the main rule of the max heap is the parent must always be greater than its children nodes. So again, the heapify function will be called here for the left subtree. Okay, and after that it will find out which one has the largest value, either 5 or 6. Now 6 has the largest value, so 2 will be swapped with it. And in the last figure, as you can see here, now this complete binary tree is actually a max heap now. It has converted to the max heap now. So as you can see, to convert the max heap, to convert a complete binary tree into max heap, we have to call the heapify function multiple times. And that single heapify function will again recursively call the the heapify the recursively call the heapify function, that is itself, again and again until the complete rule of law is established from the root node to the leaf node, and those rules of law actually are the rules certified or being maintained by the max heap law or are listed in max heap law. So we have to implement the max heap laws to the complete tree until the complete binary tree has been converted to max heap, and this is actually our heapify algorithm. Okay, so let's go ahead with our heapify algorithm. Now, the heapify function will be called as the array will be passed which you actually want to. Then this would be, first of all, this would be a complete binary tree. That is the foremost condition. If that is not a complete binary tree, then your heapify function is not going to convert this into heap sort. It is going to convert it into some other thing, which will make no sense. Okay, so I have to be careful. And the number of element and the root node which you want to start. The root node from which you want to start. That is, if in this case I have to call the heapify, I have to first pass this complete array here, the number of element in it, that is 1 2 3 4 5 6, and the root node index. I is the index. So 1 2 3 0 1 2. So 1 will be passed if I want to heapify this particular left subtree. So this function will now try to sort this, not sort, but heapify this particular portion of your complete binary tree. Okay, so it will first assume that root node is the largest. First assume. Okay, so I have assigned the index I as the largest. Then try to find the left index of the left child and the right child. We have already done with these formulas. And then it will try to see if first the index of left is still less than n. That is, it may be possible that you have passed on the root node as 5, and it will try to calculate if the heapify function you called with this particular root node, that is 5, and if it will try to calculate its child. But as you can see here, the child don't exist. So then and there your heapify function would return that okay, we are done with it. We are done with the algorithm because we are at the leaf nodes. And leaf nodes are the smallest one, and we cannot do anything because it doesn't have any child nodes. And if it doesn't have any child nodes, so it is okay to be any value at the leaf nodes. Okay, so first we have to check whether this index is less than n or not. That is the highest number of elements. Let me again, highest number of element is 6, but you cannot say that left is less than equal to n because index is always less than the highest number of elements. So index of this particular element will not be 6, actually 5. So if it is less than 5 and the element at this index is actually greater than the largest, that is, if this, let's say at this point, if element at this point, this is your root actually 6, or in this case, let's say let I have passed this array, particular array, number of element 6, and the I equal to this, the index of this particular node. Okay, and if for the left, first we will see that if the element at this left hand side is actually greater than this element root node n, that is 2, then largest will be converted to left. That is, the pointer which is actually indicating the index of the largest element of all these is now pointing at 5 now. Okay, now next, again, first we will see if the right child exists or not, and then if the element at the right hand child is again greater than the largest. As you can see in the first step, that is this particular if clause, we have already done that. The largest has been shifted from here to here. That is 5 is now largest. So it will compare this value 6 with largest, and if it is, then largest will again be shifted to 6. So root node is this now, and largest node is this now. The only thing left is we have to swap these values. Okay, so the last part of your heapify function is if the largest is not equal to I, that is, we have found out that the root node is not actually the largest node, and as you can see, we want our parent to be the largest node than its children. So in that case, we have to swap a function called swap, a very simple function you can use. And the element at the I, that is the initial root, and element at the largest will be swapped with each other. Okay, and then heapify the complete array, the complete number of element and largest. So heapify has called heapify again. So what it is doing is we have reached here, 6 is there, 2 is here, but if it has some childs here like this, then we are not sure if that 2 fits there or not, if it is greater than or not. Okay, so then heapify will be applied to the lower part of this tree if it exists. Like in this case, first we have applied the heapify function here. Okay, the largest is pointing here. Now this 2 doesn't fits according to the rules of max heap. So again, this particular heapify function which has been applied to the this particular node here will actually call the heapify function again. That is, it will call itself to sort, not to sort, but to convert this left subtree into a heap, max heap. Okay, so it will not stop until it has reached the leaf node. Now it has, if after this element, now as you can see, we have reached here, and in this case, the largest will be pointing to this particular element because 6 is the largest element, so the largest pointer will be pointing to this particular element. In that case, as we can go no further, the recursive calls will stop. That is your base case. Okay, so I think you have understood why a particular heap is calling itself. It will not stop until it has reached the leaf nodes. And if it has reached the leaf node, in that case, you can say that your binary tree, your complete binary tree is now converted to max heap. Okay, so I'll stop here right now. Tomorrow, for first 5 minutes, I will try to again revise the building of the max heap, and after that, if you are comfortable with the building of the max heap, I think you will be more than comfortable with the heap sort, because heap sort is just an application of max heap. As you can try, as you have already figured out that what max heap will does it will try to put the largest element in the array to the first index, and if I can put out that first index and store it to the last index of any other array of same length, then by doing that again, that is heapifying, putting out or taking out the root node, then storing it in the array. The next array in which I am going to store the elements, they are actually going to be a sorted one. So we'll see that in the next lecture. Don't try to confuse yourself now. Thank you.